In this video, we're going to start section 3 by introducing Bronsted-Lowry acids and bases, and to discuss the flow of electron density, that is, the curved arrow notation that we commonly use when showing reaction mechanisms. We start with acids and bases because, in many ways, it represents a fairly simplified version of an organic reaction. So in general, Bronsted-Lowry acid-base reactions are proton transfer reactions. They involve the transfer of a proton from the acid to the base. And so if we define the Bronsted-Lowry acid, we define it as a compound that can serve as a proton donor, whereas the Bronsted-Lowry base is a compound that can serve as a proton acceptor. So as you can see in this example, the acid is hydrogen chloride. It's going to act as our proton donor. And the base in this example is a molecule of water, which will act as our proton acceptor. We'll discuss this in section 3.2, but we can draw a curved arrow to represent the movement of electrons from the base, and that of a lone pair, used to form a new bond with hydrogen in HCl. Now, hydrogen can only form one bond with another atom, and so therefore, as that bond is forming, this bond is breaking. And so the net result is we end up with the hydronium ion, H3O+, and the chloride ion as well. And so this is a typical example of an acid-base reaction. And again, the overall change is that of a proton transfer from the acid to the base. Now, when we look at the product state of this acid-base reaction, we have terms to describe the resulting products. A conjugate acid is called the product that results when a base is protonated, whereas the conjugate base is the product that results when an acid is deprotonated. So the terms that we typically refer to in acid-base reactions is we say that this species here, this molecule here, is the conjugate acid of the base, and that the conjugate base is from the acid. And so this hydroxide ion would be considered the conjugate base of the acid. It is the product upon which the acid has lost its proton, whereas the conjugate acid is the product of the base accepting that proton. And similarly, we can use a curved arrow formalism to represent the transfer of the proton. We can draw a curved arrow from, in this case, the tertiary butoxide, so an oxide, towards the hydrogen atom attached to oxygen in this water molecule, and again, breaking the OH bond to result in the formation of the new conjugate acid, which is a tertiary butyl alcohol, and the resulting conjugate base, which is the hydroxide ion. Now, again, these curved arrows are representing electron flow, electron movement, and that is the basis for this formalism. The net change is the loss of a proton from water, which is accepted by the base. And I say proton because what is not transferred is any electrons that were originally associated with the hydrogen atom, the single electron. So what in fact is transferred is what we often refer to as a proton, which is H+, because both electrons in this OH bond now become a lone pair on oxygen as a part of the hydroxide. So in effect, what's been transferred has been only the proton, because it's the lone pair from the oxide that was used to form this new OH bond. So it's important to remember that proton transfers involve the transfer of a proton, H+, from one molecule to another, whereas the hydrogen atom is the atomic hydrogen with its single electron, and we'll see later on in the course when hydrogen takes on an additional electron, we refer to it as the hydride. But for now, for acid-base reactions, we're referring to the transfer of a proton from the acid to the base, which is the result of the electron flow from the base to that proton. So as we just saw in the last couple examples, these reactions are all accomplished via a flow of electron density or electron movement. So the motion of electrons between molecules is vital. It's critical to the formation of new products. And reaction mechanisms are described by this electron flow, and we used curved arrow notation to describe those electrons flowing from one source to another. Now the flow of electron density, as we've seen, is illustrated by these curved arrows, with the tail of the arrow always starting from a source of electron density. As we saw in the previous videos, that can be a lone pair or a pi bond. And as well, the head of the curved arrow is always going to be pointing in the direction of where the electrons are flowing to, where they are being shared with another atom. So in this way, curved arrows are used to illustrate what we call a reaction mechanism. They basically show how a reaction occurs in terms of the motion of electrons. So again, as you can see in this example, we have a base present, the hydroxide ion, OH-, and a lone pair of electrons on the oxygen atom are being donated in the formation of a new bond with the proton in this carboxylic acid. The net result is that we form a molecule of water and we form a acetate ion, which is shown here. So again, the conjugate acid of the base, it's the resulting product when the base accepts a proton, whereas the conjugate base of the acid is the product upon which is formed when an acid loses its proton to the base, or donates its proton to the base. So we ask the question, how do products of a reaction form? Those details are what we refer to as the reaction mechanism. And a reaction mechanism is a series of intermediates and curved arrows that show how the reaction occurs in terms of the motion of electrons. And these mechanisms are very important to our understanding of organic chemistry. They represent the core of organic chemistry. We often will categorize and classify organic chem based on the types of reaction mechanisms that organic molecules undergo. So in our research labs, we're continually proposing and comparing mechanisms and trying really to discover trends and patterns that define this behavior that we observe of the electrons as they're involved in these atomic and molecular systems. And it's these trends and patterns that enable us to predict how electron density flows and to explain how new reactions and new products are formed and come about. So in many ways, reaction mechanisms help us to organize the literally thousands of reactions that can occur in synthetic labs and occur in nature. And so you'll see in this course, we'll cover some of the more prominent reaction mechanisms that we use to describe the transformations of organic molecules with certain functionalities to product states which evolve to new functionalities. So functional group transformations will be a key area of the reactions that we cover in this course. So as a closing point, there are literally millions of reactions, but fortunately, there are a relatively small number of basic mechanisms that describe these reactions in organic chem. So again, looking at another example of a proton transfer reaction, an acid-base reaction, if we had this example of water in the presence of methoxide, as we'll talk about later in this chapter, the methoxide relative to water is a stronger base. It's a better acceptor of a proton because it has electron density to share with this molecular partner, water. So in this example, as we've seen previously, the lone pair on the oxide is going to donate itself in the formation of a new OH bond. And as a result of that bond being formed, the OH bond in the proton donor, the acid, the water molecule, that bond will break to form the hydroxide ion. And so again, the hydroxide ion would be considered the conjugate base of the acid. And methanol, the product methanol, the alcohol that's formed in this reaction, would be considered the conjugate acid of the base. Now, a common example of an acid-base reaction that can help in the treatment of heartburn is the use of antacids. So antacids in general are mild bases, and these are used to neutralize excess hydrochloric acid produced by the stomach. And so a common example of an antacid is Alka-Seltzer, which chemical structure of the active ingredient is sodium bicarbonate. So sodium bicarbonate in the presence of HCl will form carbonic acid and the chloride ion. And so again, this is a proton transfer reaction whereby HCl is your proton donor and the bicarbonate ion is your proton acceptor. And again, we see that it's the electron flow from a lone pair on oxygen towards the hydrogen atom, which will be transferred as a proton, because both electrons in this covalent HCl bond will reside on the chloride ion as a side product. So the net result is the formation of carbonic acid, and carbonic acid will then undergo intramolecular reaction in which it will be converted to CO2 and water. So, of course, when you're taking antacids, it's very likely that there'll be a little bit of CO2 released, which will result in a bit of burping. So if you have any questions about acid-base reactions, which, as we've said, is an example of a proton transfer reaction, or if you have any questions about how curved arrows are used to describe these reactions, by all means, send me an email or start a discussion in our forum. Thank you.